Welcome everybody. Good afternoon. And okay, so I see the students and the Professor Watanabe in the UT side, small screen here. Okay, so hello everybody in Japan. Okay, so yeah, good afternoon. Okay, we are in the same time zone. Okay, all right. All right, so this is the last part of this class, the practice session on the DFT using the VASP program. Okay, so we are going to have the 4-week classes from including today, and today we are going to deal with these atomic structures and the basic parameters used in the DFT calculations. And for the next week and next week, we are going to have the break because of the Korean holiday, Buddha's birthday, and also maybe I heard that there is some types of the holiday or break in Japan, and so we have no classes for these 2 weeks. And then we are going to continue with the energy band structures. And then I will, next June 12th, I will visit UT site and teach about the defect. And the last class will be about the molecular dynamic simulations. So, all right, so actually this is my first time to have this kind of the mixed the theory and the practice session, and so I'm not sure how smooth will be the practice session, but we'll try our best. Okay, so in the first part of this class, first maybe about 1 hour or so, I will teach you about the basic things about the DFT calculations, basic parameters that is actually used in the computational setup. And many of the materials are actually already been discussed in the previous classes by Professor Watanabe, but I am going to summarize some of them here. And then we have a break about 15 minutes, and then we are going to continue have the practice session. Then I suppose that the students in the UT side also can access to their own clusters, and I have sent to you some basic info files, so maybe you can follow what the TA will tell you. All right. So okay. So the title of this theory session is about the key concept in DFT calculations, and so basically what we are doing in this type of the research is actually we are doing the 2 things. One is the computation, and the other is we are going to analyze on the result. Okay, so computation means that we are going to solve some equations that is basically close to the Schrödinger equation, and so it has 2 parts, kinetic energy and also the potential energy part. Okay, so this is the eigenvalue problem, and this E is the energy, and this psi is the thing about the wave function. All right, but here the complicated thing is that this potential is actually 3-dimensional potential, and it is also the periodic potential, because we are basically assuming some crystalline structures of the material, so the potential is actually periodic potential. And this potential that is felt by electrons are actually is split into 3 parts. The first one is the ion potential. This is the Coulombic interaction between the nucleus and electrons, which is about 1/r. And the VH is the Hartree potential, which is correspond to the Coulomb interaction between the electrons. But it is a classical electron Coulomb-Coulomb interaction. All right. So this is classical interaction. These 2 are ion, and the VH are the classical interaction. The last part, the exchange correlation. This is actually this stems from the quantum mechanical effect, and it reflects this indistinguishabilities between the electrons, and also the Pauli exclusion principle and this exchange principles. Everything is just dumped into this exchange correlation potential part. This is the formulas that we comes from the density functional theory calculations, but we are somehow this is simplified into 1 particle Schrödinger equations. Okay, so all right, so we are going to solve these types of the Schrödinger equations in three-dimensional structure. All right, so the list of the content is as follows: the lattice spectral, and then reciprocal lattice, and then planar expansion, Stope potential capable sampling, and the overall point structure. I will tell you each of them one by one. Okay, so first, lattice spectral and atomic structures. All right, so maybe you know that this crystal is basically a three-dimensional complete ordering of the atoms. All right, so you see here some approximation structures, and this minimum periodic unit is called the unit cell. All right, and so mathematically the system is invariant because we are assuming the infinite system. So the system is invariant all the period on the translation, arbitrary translation. That is the integer multiplication of this A1, A2, A3. These three vectors are so called the lattice specters, which defines the basic repeating unit of the crystals. Okay, so I think that you already know familiar with this kind of the notations. So the crystals that we have, the actual crystal is actually the lattice specters. On top of the lattice spectra, there are the basis atoms that is making the unit cell. All right. Okay, so the lattice. So let's talk about this in more detail in the example of the appreciation structures, the most simple structure. This is the so-called conventional cell of the phase appreciation structures, and there are three lattice vectors: A1, A2, and A3 vector. Okay, so the lattice vectors in the Cartesian coordinate, has this simple form. Okay, so along the x, y, and the g direction. And here the this A is called the lattice parameter. Okay, the length of this cubic cell. And this A1, A2, A3 defines the basic periodic structure. And atoms within the unit cell, there are actually 4 atoms in this conventional cell of the appreciation. Okay, so one in that corner or the origin, and there are 3 others at each face. Okay, so there are 2 ways that we represent these basis atoms. The first one is so-called internal or relative coordinates. This is the with respect to these 3 lattice vectors A1, A2, and A3. Okay, so for example, this is the second atom at the bottom here. This is actually the half of the A1 plus half of the A2. You can see here. Okay, so its internal or relative coordinate is half, half, and 0. Okay, likewise, 3 and 4 atoms can be represented like this. Okay, as an internal coordinate. On the other hand, there is an absolute coordinate, which is the x, y, g, and has the absolute some sort of the units. And so, for example, the second atom is in the absolute or Cartesian coordinate. It is represented as the half of the A and half of the A and comma 0. Okay, so this is the x, y, g Cartesian coordinate. Okay, so this is called absolute or Cartesian coordinate. So the program supports these 2 types of the representation of the basis atom, the position of the basis atom. All right, and you may know that in the case of the appreciation structures, there are another way, or the more simple way to represent this cell, and this is a primitive cell. In this case, it's A1 and A2, these 3 vectors are pointing to the atoms at the face, at each face. So in this case, the lattice vector is represented like this, and there's only one basis atom at the center or at the corner or at the origin. Okay, so by simply repeating these one atoms with these lattice vectors, you can represent whole lattice of the appreciation structure. All right, and one thing that you may remember is that in the coordinate system should always follow the right-hand rule, which means that the first and the second lattice vectors, then you apply this. Okay, so you apply this right-hand rule. Then the third lattice vector should be aligned toward this direction. If it goes the other way, then it is following the left-hand rule. Okay, so the first and the second lattice vector, or if you apply the cross vector or the right-hand rule, then the third the vector should be aligned the direction of your thumb. Okay, so that is what we mean by the right-hand rule. So the usual x, y, g coordinate is, of course, the right-hand rule. If you write this x-axis, y-axis, and z-axis is one by one, then it follows the right-hand rule. All right, so then we'll talk about the reciprocal lattice, which is very important in our periodic structures. Okay, so the definition of this reciprocal lattice, or the reciprocal space, or sometimes K-space, is the lattice point that is made by the three lattice vectors B1 and B2 and B3. Okay, like you know, in the real space, A1, A2, A3 represent the periodicity in the real space. In the reciprocal space, this B1, B2, B3 is representing the periodic structure of the K-space. This B1, B2, B3 is obtained by this cross product of the A1, A2, and A3. So this is mathematical definition. Okay, so these are called the reciprocal lattice vectors. So, for example, if we apply this rule or this reciprocal lattice to the cubic structures, then this A1, A2, and A3 vectors are converted into B1 and B2, B3 in the same cubic structures, but its lattice parameter is scaled down from the A, not scaled down, but it changes from the A to 2 pi over A. Okay, so this is why it is called reciprocal relation. So the reciprocal length is actually inverse relations in the length of the reciprocal lattice. This is why it is called the reciprocal lattice. Okay, so if your lattice vector is big in the real space, then in the reciprocal space the length should shrink. All right, and also if you apply this formula to the appreciation lattice vectors, then this B1, B2, B3 represent. Okay, oh, sorry, this is also yes down here. Okay. So this converted into the BCC structures, again the lattice parameter A is changing to the 2 pi over A. Okay, all right. So this is the definition of the reciprocal space. Okay, then from the reciprocal lattice, we can define this Brillouin zone over the first Brillouin zone, which is the first and second and third, but the first Brillouin zone is most important to us. So the primitive cell in the reciprocal space, the definition of this first Brillouin zone is the primitive cell in the reciprocal space whose boundaries are set by intersecting planes or lines, in this case of the two-dimensional system, connecting the points in the reciprocal space. Okay, so what it means is that you can, so for in the example of the one-dimensional structures, the real space, the lattice is as follows. So as the length of the lattice vector, lattice parameter is L. Okay, so every point, the lattice point are repeated and like this. And then the K-space is converted into the same the periodic lattice point, but the length of the lattice parameter is shifted to 2 pi over L. Okay, so the first Brillouin zone means that around the center or the origin, you can draw these intersecting lines. That's connecting these two. You can draw these intersecting the perpendicular lines to dashed lines, and so the region within these two boundaries are called the first Brillouin zone of the reciprocal space. Okay. In high dimensional, for example, in the two-dimensional space, the square lattice also converted into the square lattice in the K-space, and in this case, around the origin, you can also draw the several intersecting the lines. Okay, and those the region that is in this that is innermost region. This is called the first Brillouin zone. Okay, and in the case of the hexagonal lattice, we can do also a similar thing. All right. So the K point in the first Brillouin zone have the given lattice point as their first nearest neighbor. Okay. All right. Which means that the K point in this first Brillouin zone actually is the closest to the specific K point, or in this case at the origin. All right. So the most complicated thing, that's the three-dimensional structures. For example, in the case of the appreciation structures, you have these species structures in the K space, then you can draw the plane, in this case, the perpendicular intersecting planes connecting each of the, the points. And then you can imagine that innermost regions are these kind of structures. Okay, so this is a dodecahedron, maybe I might right. So this is a yes, something like that. Some truncated octahedron structures. I remember that this is a truncated octahedron. So you have the octahedron structures, but if you cut each corners, then you have this shape. Okay, so this is called the truncated octahedron structure. All right, so this is the first Lagrangian of the efficient structure. All right. All right. So so if you can take this one of this first Lagrangian here, okay. So then some of these points within this first Lagrangian actually they are equivalent because of the symmetry. For example, if you have the full symmetry of the approximation structures, then your x and y and g axes are all equivalent. All right. So which means that this point at the center of this square here is equivalent to other points at the center of the square. All right. So in this way, you can actually remove all those points that is symmetrically equivalent, and the remaining part of the first Lagrangian, which does not correspond to any other points under the symmetric operations that you have in the crystal, is called irreducible Lagrangian. Okay, so meaning that some other K points are actually, by applying some sort of the symmetry, you can actually overlap overlap the point with the point, a certain point in the irreducible Lagrangian, or technically, okay, so physically they are equivalent. All right. Okay, so you will see that how it applies to our, it can be applied in our calculation later. And we deal with K point sampling. All right, and also this specific K point that especially have the high symmetry points are called special points, and some of the, and each of these points are have their own its own name. Okay, so the gamma point always meaning the center of the Lagrangian, and X point usually indicates the point at the extreme of along the x-axis in this way. All right, but the specific names always follows a different, is different among the different symmetry group. Okay, then we will move to this plane of expansion and cutoff energy. Okay, so if you have any question, then okay, don't hesitate to interrupt me. And also maybe I can communicate with the students in the UT side. Am I right? So so if you have any question, then yeah, you can just break in and you can make a speech. All right? Okay. All right. So in our system, the potential is a periodic system. So because of this crystal symmetry, in this case, we have the well-known, the so-called Bloch theorem, which states that wave functions are represented always follow a certain specific form. So in the case, this is the simple example in the one-dimensional structure. So in a one-dimensional structure, so along the x direction, this psi x is represented like this shape, okay, exponential ikx times ux, and this ux is actually this periodic, satisfies periodic boundary condition, the same periodic boundary condition that you have in the crystal, okay? And here the k, so wave vector k is any vector in the first Lagrangian, okay? So the solution of the Schrödinger equation under the periodic potential always follows this form, okay? Psi x equals to exponential ikx times ux, and ux is the periodic potential, a periodic function, all right? So, in this case, arbitrary vector in the first Lagrangian. All right, so since the u is the periodic function, then you can expand it using the Fourier series. Okay, so any periodic function can be represented as the sum of the Fourier series. All right, So this ux is actually exponential il 2n pi over l times x. So in the case of the n is minus infinite to the plus infinite. Okay, so this is the usual the Fourier series with applied for the function with the periodicity of the L. All right, so this is the complex complex version of the Fourier series. And here you can notice that this part is actually equal to the lattice point in the reciprocal space. Okay, if you go back to the previous slide. Okay, so here, all right, so it's one-dimensional system with lattice parameter of the L. Then the reciprocal lattice is the lattice point is 0, 2 pi over L, 4 pi over L. So this is a reciprocal lattice point. And then you can see that the term, the wave vector appears in this Fourier series exactly those points in the reciprocal space. All right. So this is actually this is not a coincidence, but this is the general for any periodic system. All right. Okay. So basically this the Fourier expansion is the sum of the coefficient times exponential I g x. G is at any point in the reciprocal space. All right. Since the g is the infinite, minus infinite to plus infinite, there are infinite number of the g vectors, then in order to deal with within the computation, we have to cut out some of the points, and we cut them on the basis of the magnitude of the magnitude of the g vector. Okay, so for instance, for the specific the g, then you can assign some of the energy, like you get free electron energy. How about square times g square over 2m? Then within a certain cutoff energy, you can only contain those terms that is within a certain cutoff energy or certain g cut. Okay, here, all right. So this is what we are doing in the actual computation. Okay, so in a three-dimensional structures, this you can simply expand it into the three-dimensional by making this R as a three-dimensional vector, and also the same types of the expansion. Here the G is equal to any point in the reciprocal space, and again you have this certain you have the cut contain only those G vectors is magnitude that is less than the cutoff wave vector. All right. So in order to so how we can determine this G cut? Okay, so here this is an example showing the relation between G cut and the wave function shape. Okay, so in this example, so this lattice periodicity is 4 angstrom, all right, and you have two types of the periodic function. One is this shape, and the second one is more localized, or this is more dispersed, this is more localized. So if you expand this function with the Fourier series that we have shown in the previous slide, then this is the magnitude of the coefficient Ag. This is n equals 0 term, n equals 1, 2, 3, etc. So you can see that as this G goes up, then the magnitude of Ag decays very rapidly. So therefore, you can safely cut out those contributions of the higher order terms. All right. So you can apply a certain cutoff, okay, to ignore entirely the rest of the G vectors. But in this case, with the wave functions or some functions that is more localized, you can see that it decays more slowly compared to the first one. All right. And so if we are going to apply the cutoff energy, you can see that you have to slightly increase your cutoff energy or G cut in order to describe this wave function accurately. All right. So this is a general rule. So higher cutoff energy is required for the localized states, and this cutoff energy depends on the extent of the localization. All right. But one thing that is very convenient for us is that this localization is fairly intrinsic to each element, because this localization is most important around the center of the atom. So, but the chemical bonding is between the atoms. Therefore, each element has its own specific cutoff energy that is necessary to describe its wave function accurately. All right? So it does not depend on the system, but it is more depends on the which atoms you have in your system. All right? Okay, so but if there are certain different elements, so some of the atoms will have the more localized wave function, or some of the atoms will have more delocalized wave function. In this case, we always use the maximum cutoff energy for the more accurate the result. All right. Okay. So, let's move on to pseudopotential. All right. So, why we need pseudopotentials? Okay. So this starts from this investigation of the atomic orbitals for each atom. So this is the radial part of the wave function and energies for the zinc. So the zinc has the atomic number of 13. So there are 13 electrons in zinc, and this is 1s orbital. Okay, so this is 0 is the center of the zinc atom, and this is the radial distance from the nucleus, and this is 1s orbital, and this is 2s orbital. This is 2s and 2p. This is 3s and 3p. And this blue one is 3d orbital, and this is 4s orbital. All right, and for the comparison, this dashed line is the zinc distance in metal. All right, so it's typical the atomic distance. So typically atoms are at this distance. Okay, it's actually half of this distance. The zinc distance in metal is 2.9 angstrom. So this dashed line is actually the half of the distance from the another atom. All right. So you can see that many of the electrons, especially those electrons at the core, also core electrons, these wave functions are very much localized. All right. So it does not sense any presence of the atoms in the nearby, unless you extremely compress your system. Okay. So those core electrons are very much pretty much insensitive to the presence of the other atoms. On the other hand, the electrons at the outer shell, or the so-called balanced electrons, its wave functions are actually touches or can be overlapped with wave functions of the wave functions from the other atoms, and the same is for the 4s orbital here. And so, therefore, it contributes to the forming the chemical bonding. All right. And also, so basically, it's localized. The core electrons are too much localized in space to contribute to any chemical bonding. And also, in terms of the energy, if you look at this energy, so one is of this minus 700 electron volt, 2s and 2p, they are 70 to 80 electron volt, and also 3s, 3p, they are about minus 5 to 10 electron volt, which is very much low in energy. So the chemical bonding is usually on the order of the 1 to the couple of the electrons. So compared to that energy scale, you can see that these core electrons are too much low. I mean, it's too much stable to form, to have any gain from forming the chemical bonding. So because of these two reasons, the core electrons, we can simply say that these core electrons do not contribute to any chemical bonding, or to some approximation, to a good approximation. Okay. So then how can so you want to remove those core electrons completely from the computation, but it is not so easy. So people have found that there is a there's technique to remove the effect of the core electrons, or entirely ignore these core electrons. This is called the pseudopotential. Okay, so it starts from this way. So the solid lines are actually real wave function. This is the center, and this is the real distance, and this is the real wave function. All right. Then you construct this pseudo wave function, because inside there is a nodal, very rapidly varying wave function or nodal structures around the core, because of its potential is going down. So because in order to increase the kinetic energy, there is usually have the more nodes around the near the nucleus. But these oscillations actually do not influence any of the chemical bonding because it's too much close to the core electrons or core atomic cores, and therefore we can pseudize, approximately pseudize this wave function shape as like the dashed way, but it does not compromise any of the nature of the chemical bonding. All right, so which means that in order to have this pseudo wave function as the eigenvalue function, you have to deform your potential. Instead of the 1 over the r, you have to sum of the finite potential, that has this pseudo wave function as the eigenfunction. All right, so you change your wave function and also you change your potential near a certain cutoff radius, which is pretty much close to the nucleus, and so it does not overlap. So between the atoms, these core regions are actually separate. They do not overlap. Okay, so by doing this kind of pseudization, the advantages are the core states are automatically eliminated because you have eliminated this one of all these strong potentials in the nucleus, so you are eliminating the core electrons entirely. And also, nodal structures of the wave functions are much simplified, which means that, as we've seen before, such a strong oscillations always requires high cutoff energy. But by making the smooth wave function, you can actually reduce your cutoff energy or dimension of your basis function, or your computation cost is greatly much saved. But there are also downside of this such an approximation. So for example, you have the non-local potentials is a technical effect. So which is non-local potentials actually more tricky to deal with numerically. All right, and also in the case of the magnetic interactions, the interactions, for example, hyperfine splitting, it is sensitive to the overlap with the core electrons. But since you have the pseudized wave function at the core side, therefore this pseudo potential is not so much accurate when you are interested in the very much sensitive magnetic interaction, for example, hyperfine splitting. All right, but in most of the cases when we are interested in the material properties, then this is approximation is a very much economic, and also you do not compromise on the chemical the accuracy. All right. Okay, so we have the many reasons to employ the pseudo potential approach. There are several types of pseudo potentials like non-conserving and ultra-soft and PAW. And okay, so I'm not going to details, but these days, since the VASP fully support these PAW pseudo potentials, and so it is now becomes most popular. In my time, when I was in a grade students, I mostly used just non-conserving potentials, but these days PAW is used everywhere. All right, but basically the same pseudization scheme. All right, and so one thing that we have maybe remember for more sophisticated calculation is that actually you can have different types of pseudization. For example, in the case of titanium atoms, you can, so 1s, 2s, 2p, it is out of question that they are the core electrons. And the 4s, 3d, okay, they are, of course, they are valence electrons. But it is a little bit subtle that this is 3s and 3p, whether they are core electrons or the valence electrons. So, by putting these two 3s and 3p electrons into the valence electrons, then you have the more accurate description of the core electrons. All right, so actually, as you have the less degree of the approximation, so you are doing the more accurate calculations. So this is more accurate, but it increases your computational cost because you have the more electrons in your system, and also this core electrons are actually require higher cutoff energy. Okay, but so you can actually put these 3s and 3p orbitals into the core electrons and entirely ignore in the calculations, and adopt this 3s and 3d, only this 3s and 4s and 3d as the valence electrons. In this case, you have a computation much more efficient, but is less accurate than this the first Pseudization. All right. So this kind of the orbitals, which can be either into the core or the valence electrons, they are called the semi-core potential, semi-core orbitals. Okay. And in the VASP, you can they distinguish these different two types of the Pseudization by putting this subscript like a S way, which means that this S is the valence. Okay, 3s and 3p is included, and 3s and 3p they are included in the valence. So this is what they mean by this SV. And the default, more efficient version is usually does not have any tag. All right. Sometimes you have this S and H tag, which means that you have these soft or hard. Soft and hard means that whether you so it is about this cutoff energy, cutoff radius. So if you take this smaller cutoff radius, then you have the more accurate Pseudization. On the other hand, okay, so you have the more accurate Pseudization, but if you have the longer or larger cutoff radius, then you are doing more Pseudization. All right, so it's less accurate, but it's it requires smaller cutoff energy. Therefore, it is the faster. All right. So depending on your situation, you can adopt the different types of superpotential. But know that there's no free lunch. Okay, you are always it's between this compromise between the accuracy versus computation speed. All right. All right. Okay. So let's move on. The K-point sampling. All right. Okay. So as I mentioned before, the Bloch theorem states that your wave function is, in the periodic potential, wave function is represented like that, exponential IKR times some of the periodic function, and this K is belong to any vector in the first Boolean zone. Okay, so if I put this form of the wave function into the Schrödinger equation, then you can expand your Schrödinger equation like that. Okay, now you are expanded this UR, which is the periodic part of the wave function, as the Fourier series that we have discussed just before, and so you are doing the Fourier analysis of, and you are solving this eigenvalue equation. You are converting this eigenvalue equation into the matrix equation. All right, but the one thing is that this K is arbitrary number, arbitrary vector in the first Boolean zone, which means that for each of the K point, you have the different equations. All right. So, and this K can be any vector. So, in order to have the exact solution, which means that you have to solve infinite set of the equations. All right, with the different K vectors. Right, which is impossible to do within computationally. All right. So, what we do here is that instead of this, this infinite set of the K, we are approximating this K point approximate by a finite sampling in the first Boolean zone. That is called K point sampling. All right. Instead of using the every K vector, but you are sampling certain points in the first Boolean zone. Okay. So for example, this is the two-dimensional scale lattice. Okay. This is the first Boolean zone. Okay. So instead of the whole region, you are sampling these points on a regular mesh. Okay, so that is represented by this blue point here. All right. So by increasing the density or the size of the mesh point, you are doing more and more accurate calculations. All right. So, but at some point, you will see that your result does not change anymore. Then you are stopped there, and you have the enough number of the K points there. Okay, so here we have this 4x4 K point mesh in the first Boolean zone. And let's say that because of symmetry, the shaded region in blue, they are correspond to irreducible Boolean zone. Okay, which means that every other points are actually symmetrically equivalent to this point in the irreducible Boolean zone. Which means that instead of the 16 point on this 4x4 mesh, you just need to compute on just these three points here, K1 and K2 and K3. All right, so it is much more convenient if you have the high symmetry of your crystal. Then you don't need to do the whole computation on every K point on the regular mesh, but you can reduce it by a significant the fraction. All right, so computational cost is usually proportional to the number of K because you have to solve each set of the equation for each K point. So usually your computational cost increases scale with the number of the K points. It is so brilliant done. But sometimes, for example, in the case of the hybrid functional calculations, then your computational cost is greatly increases, like an NK square instead of the NK. All right, so and of course the higher density of the K point gives more accurate result. Okay, so but the number increases very rapidly in three-dimensional structure. Okay, so therefore, by doing the sum of the convergence test, you always take this minimum number of the K point. All right, and this appropriate K point density, it depends on the cell size, because if you have the big cell size, then your reciprocal space will be smaller. Okay, then you need to take the smaller number will be enough. But if your cell is small, then your reciprocal space will be big. Then you have to increase your K point density and the K point, the sampling number of the K point. All right. Okay, so all right, and also the electronic structure. So whether you have the insulating system or the metallic system, so it depends on your the K point density. Also depends on the electronic structure. All right, and so there are several ways to take this K point in a regular mesh, or even within the regular mesh. Where is the where to put this origin of the mesh? It depends on your choice. But most favored choice is called the Monkhorst Peck grid, which is the follows the name two researchers, Monkhorst and Peck. So they suggested that a long time ago that in the case of the even numbers, for example 2 by 2, it is better to take this gamma point or the origin at the center of each of the square, the mesh, and sample those cross points. All right. But in the case of the odd number, then it is better to take this mesh overlap with the center or the gamma point. And so therefore, in the case of the 4 by 4, this is the Monkhorst Peck grid. So depending on whether it is the even number or odd number, your gamma point is maximally avoided or it is included within the mesh. All right. So this is one choice. But sometimes you may use this so-called gamma centered grid, which is in any case, regardless of the sampling, the density, the gamma point is always included. Okay. So sometimes for specific purpose, this gamma centered grids sometimes it converges faster. Okay. So it is favored over the Monkhorst Peck, but for the general purpose, and the default setting of the and by default, I recommend you to use this Monkhorst Peck grid. All right, and about this K point sampling is always requires so-called K point smearing. Okay, so in the next slide, I will tell you why this is needed. For example, this is the K along. This is the K point, okay, and this is the eigenvalue or so-called the band structures, and this is the and this is the red one, and this is next higher the band, and this is the dashed lines Fermi level. So electrons are occupied up to this Fermi level, but so suppose that you have sampled these 2 points, okay, so here and here, then you have this eigenvalue, and at this K point you have these 2 eigenvalue and you have this 2 eigenvalue. All right, so without any smearing, or if you just take these 4 points literally, then this Fermi level means that you have this occupation of the these 2 points are occupied 100%, and this is completely empty. All right, which means that you are occupying the lower band 100% and this higher band 0%. However, because this way the band structures are actually is there some of the dispersive, therefore it is better to expect that there is a fractional occupation in the higher band, like for example 20%, and therefore this lower band has only 80% fractional occupation. So this is a more reasonable choice. But if there's no smearing, then you have only 100% occupation and 0% occupation. So in order to avoid such a the sampling problem, what we do is you have somehow the smear the energy eigenvalue of this around given eigenvalue, and you say therefore you can occupy at this point this higher eigenvalue has some of the extent into the Fermi level, therefore it will have a certain amount of the occupation number. All right, so in this way you are somehow reflecting considering this band dispersion. All right, so it is always better to have a certain amount of the smearing for the finite k-point sampling. Of course, the most accurate data is given by extremely large of the k-point and no smearing, but this is not reasonable or computationally feasible, and therefore we always have this both k-point sampling and smearing. All right, so the default setting, so there are several types of the smearing scheme, but what I favor actually most, the BAS recommends this math phasor Paxton, but I personally, from my experience, I usually favor this Gaussian smearing with the width about 0.1 or 0.2 electron, but that's generally gives you your reasonable value. But for the specific cases, you need to take some of the cautions, and you follow this the manual. Then you will see that more detailed control of the k-point smearing. All right, so this is an example of the k-point convergence with respect to the k-point along the one direction. So you can see that with the different types of so one thing that I have missed was that there was one type of the smearing, so-called the tetrahedron method. So in this case, you are actually do not smear, but you are somehow interpolating your eigenvalue, and you are estimating your band structure explicitly. So it will give, if you have the enough number of the k-point, this tetrahedron method is very much accurate. But also, in many cases, since it interpolated band structure, so it usually gives you a nice figure of the density of state. Okay, and so it is only recommended for the bulk structures where you can increase your k-point without increasing much of the computational cost. All right, so this compares with the convergence of the energy with respect to the k-point with the different types of the smearing scheme. Okay, so this one is mathematical Paxton 0.2 electron volt, and this is the okay, so this one, and this is Gaussian of the 0.01, and the Gaussian width of the 0.02, and this one is the tetrahedron. Okay, so you can by looking at so they are pretty much similar because of this so simple system, and so by a certain criterion you can take your the necessary k-points by taking some of the by applying some of the convergence criteria. But this k-point convergence differs or depends on your system, so you better to check each convergence in every calculations independently. All right, so I think I have pretty much discussed about some of the technical key concept in the calculations. So we will now overview about the general program structures. So the density functional theory, what is actually comes from this, it starts from the many-body Schrödinger equation. Okay, so since this many-body Schrödinger equation is so difficult to calculate, so we apply so-called from within the density functional theory, we apply local density approximation or gradient approximations and or GGA, and we simplify this many-body equations into one body, much simpler Kohn-Sham equations, and this is what we are solving. And as I mentioned in the beginning, there are three parts: this ionic part and Hartree part and exchange correlation part. All right, and this ionic part is approximated by the pseudo potentials, and this Coulomb potential is included per se. And about this exchange correlation potential, originally within the density functional theory, this exchange correlation potential is actually the functional, not the density function, which means that you have some of the which it gives you, so given a certain density function, then a certain number exchange correlation energy will come out. So this exchange correlation potential is actually a functional derivative of that exchange correlation energy. So it's very much complicated thing, and it is you cannot. It's very much difficult to get the whole form of the exchange correlation potential. So what we are doing is approximate this exchange correlation functional. In the case of the local density approximation, we are approximating this as a function of the density. Okay, and so in my time when I was in graduate student, when I started my graduate course, then this LDA was very much popular. But it is reasonable in most cases. But the problem is that it overbinding. Okay, so the chemical bonding is too strong, and also the bond length is significantly underestimated in many cases. All right, so then there is a new method was introduced, which is called the generalized gradient approximation. In this case, its exchange correlation potential depends not just on the density, but also the gradient. Also, this is not this one, but this inverse triangle, this gradient of the density. Okay, so by expanding this exchange correlation function, many things were improved very much, like binding energy and the reaction barriers are much better than the LDA, and also the bond lengths in many cases are more accurate than LDA. All right, but the technical problem is that it requires a higher cutoff energy, a slightly higher cutoff energy, and also the convergence is a little bit slower. All right, and there are several forms of the GGA. So unlike the LDA, GGA, depending on how you treat this, some of the functional form, then there are different variations. And the most popular one is the PBE, which is the very small number of the empirical parameters. All right, okay. And so, but one very important thing about this Kohn-Sham equation is that the density here is actually given by the wave function phi. All right, so density is the sum of the square of the wave function, that is sum over every electrons occupied orbitals. All right, but this is strange. So your problem or operator actually depends on the solution. All right, so this is the self-consistent equations. Okay, so you have the solution, and from the solution you construct this density, and you then construct this second order Schrödinger equation, these Kohn-Sham equations, and you solve again. And if your result is the same as the initial wave function, then now you can say that your equation is self-consistent and you have the right solution. All right, so that defines actually the program structures. So what the usual the program procedure is like that. So you start with a certain structure, and you provide lattice spectra and basis atoms, and you are setting up the initial Kohn-Sham equations. All right, but since in this case we do not know the solution yet, and therefore we do not have no idea about what the density will be like. Okay, so initially we assume that this density is simply the sum of the atomic density, right? So the density when each atom was in an isolated configuration. So you simply add up the density, and you use it as the initial the density. It makes sense because when you make a chemical bonding, then the density near the core regions are almost the same. The only between the atoms or the bonding regions, the atoms are the density is slightly shifted or the change in many cases. Therefore, it is quite reasonable to assume that the simple sum of the atomic density as the input the density. All right, and since you have constructed this Cornish Hamiltonian, then each k point you solve the Cornish equations, all right, and you do it, one by one for each k point, the different the wave equations. If you get the different wave functions, so they are indexed as n and k. So the k is the k point, n is the band index. Okay, so from the bottom, n equals 1, 2, 3. All right, and so you are updating the wave electron density by summing over the scale of the wave functions and sum over the occupied state and also the k point. All right, and now, and so this is the output the density, and you compare this input density and output density. All right, of course in the beginning it does not agree, so you provide from the density, for the output density and the input density, you can somehow mix or slightly change your input density from the information from the output density, and you try the new the density, right? And you do the same procedure, and after 10 or 20 steps, it usually converges, right? That means that the input and output density are equal. So then in this case, we say that the self-consistency is arrived, right? Or you have your computation, your calculation was converged. So okay, so now you have the right. So what we have from this the result is that first we have the total energy, all right? So which is actually the most important thing that we get from this calculation. So total energy, or material science, or thermodynamically, it is the internal energy of your system. And besides that, we have this quantum energy level and the quantum orbitals, all right? But since they are not the exact wave function, so they are because we have already employed some steps of the approximation. So these are the single particle orbitals, so it does not exactly correspond to the actual electrons in your system, but we can actually interpret its meaning quite clearly in many cases. Therefore, so they are very much useful in interpreting or understanding the system. And also we get electron density. And besides that, we can calculate without much computation cost. We can calculate what is the force that is applied on each atom, and what is the stress tensor. All right. So, for example, if your atoms are out of equilibrium or has a certain amount of the finite the atomic force, then you can change your position of your atoms, like we have done in the classical dynamic simulations. So then we have the new coordinate or new lattice vectors that is reflecting this stress tensor, all right? And so you provide the new vectors, and you can go through once again, all right? So everything is so. In the case of the molecular dynamics simulation, usually you have just go back and forth of these two steps. But in the case of the DFT calculations, you have another iterations that to get these wave functions. All right. Okay. So I think so. This is the basic structures, and so the basic input files are reflect these informations. So the Inca file, it has in the most extensive the file that was complicated, and it contains many of the control parameters. And this postcard is the lattice spectrum and atomic position, and this postcard is a pseudopotential information, and this k point is k points that you are going to calculate in the Verlian zone. Okay, and so those are the input file. And output files are, output file is, includes most extensive information. This quantical is a finite geometry. If it did this relaxation or any simulations, this conjugate is the geometry or Posca file at the last step. And this eigenvalue is eigenvalue, and stage car is charge density, and this is density of states. We are going to look at that in the next class. The wave car contains wave functions. This O is Zi car, this is iteration information, and this pro car is the wave function that's decomposed into the atomic orbitals. All right, so they were the Bayes input file. Okay, so that's it. So that's about the Bayes key concept that is used in the practical calculations. And so, any question? Is everything clear? Okay, you can make question in Korean, then I will interpret it in English or Japanese. All right, so if there's no question, then okay, so yeah, just send me an email, okay, so whatever you have any questions. So we will have some 15-minute break, and then come back again, and we'll have the practice session. All right, so I suggest the TAs will prepare some of the technical things that is necessary to prepare the students before starting the practice session. Okay, see you soon.
Okay, so in this practice session, we will do some calculations using PASP. So in order to do calculations with PASP, you need 4 input files: postcar, podcar, kpoints, and incar. You need at least these 4 input files. So postcar file include lattice geometry information and positions of ions, and podcar file include pseudopotential for each atomic species, and kpoints specifies which kpoints we are be using in calculation, and Inca files includes several parameters. So whether we are doing MD or relaxation or something like that. So we need these 4 files in the same directory. So we will first do some calculations on silicon. So this is the unit cell of silicon. So there are 8 atoms per unit cell. The diamond structure, and we have prepared the postcard for this silicon file in this directory. So you can write this cp command to copy this postcard into the current directory. Then you can see there are postcard. And the contents of the postcard looks like this. So the first line is the comment line. So first line does not do anything, but you can write some information. For example, which postcard this is. And the second line is a number, and this is the scale factor. So if scale factor is, for example, 2, then all these cell and atom positions are scaled by 2. So it is 2 times bigger. So this scale factor is useful for calculating system in strain. So we can use, for example, 1.01 to calculate system in 1% strain. And these next 3 lines indicate lattice vectors. So the third line is A1 A vector, and the second is the B vector, and the last one is C vector. So these three lattice vector consist the system lattice, and the next line we write the element. So in this system we have only one element, but if we have several elements, we have to write them all in this line, separated by space. And the next line indicates that this silicon, there are 8 atoms of silicon in this system. So this is the number of atoms for each element. And the next line is either Cartesian or direct. So when this line is direct, then it is in fractional coordinates. That is internal coordinates or relative coordinates. And if it is in Cartesian, then it is in Cartesian coordinates or absolute coordinates. And then last 8 lines, because there are 8 atoms in this system, 8 lines indicates the positions of each atoms. So they are silicons, and one is at the origin, and the others at these positions. So this is in fractional coordinates. So 0, 0.5, 0.5 means it is at the position of 0 times A1 plus 0.5 times A2 plus 0.5 times A3 or ABC. So in order to, so you can visualize this system like this figure using a visualizer program. In this class we will be using Vesta. So you can download Postcard to your local computer using sg postcard command. Then you can open this Postcard using Vesta. So by using sg command, you can download Postcard file into the local computer, and then you can open the Postcard file using Vesta. Then you can see the structure of diamond silicon. Also, this Vesta, with this Vesta, we can read not only postcards, but other various formats. So there are, for example, CIF format, which is crystal information format. So if we open that structure file using this Vesta, then we can export this data into other formats. So for example, we can convert other file, for example, CIF file into postcard. So for example, you can export file like this, and you can either choose fractional coordinate or Cartesian coordinates. Then you can see the file is exported in the postcard format. For example, here Cartesian coordinates. There is typo in the title. This is postcard. So we now have postcard, and we now need postcard. The postcard contains the pseudopotential information and which exchange correlation functional we are using. So FAST provides these postcards. So we have prepared postcard file in this directory, so you can copy this postcard into the current directory. Postcard file can contain pseudopotential information of multiple elements. So if we are calculating multi-element system, this one postcard file contains multiple information, and then we can check which elements it is containing by using this grep titel postcard command. Then we can see there is one element, and it is silicon, and PB, we are using PB potential. Then next we need a K-points file. So K-points file specify how you are sampling the first Brilliant zone. So we can use several ways, two ways. So the first one is automatic generation using K-points file. So the contents of K-points file is really simple. If we write, the first line is also comment line, and if we write 0 on the second line, that means we are using automatic generation of K-points. And then we can choose Moncourt spec grid or gamma centered grid. So if this letter on the third line is M, then we will be sampling in Moncourt spec grid. And if this letter is G, then we are sampling K-points in gamma centered grid. And the next line, there is 3 numbers in the next line, and these 3 numbers tells the number of K-points in each direction. So there is 3 K-points in B1 direction, and also 3 points in B2 and 3 points in B3. So there will be 27 K-points. And the next line indicate optional shift. So you can just write 000 for most application. Or you can specify K-points information in the Inca file using K-spacing tag. But I would recommend using this K-points file. So the last file we need is Inca. So Inca file specifies calculation details. So for example, this I smear indicates the smearing method, such as Gaussian or Fermi smearing or something like that. And sigma indicates sigma in the Gaussian smearing. So for insulator or semiconductor, we recommend using ICMR 0, which is Gaussian smearing, and sigma equals 0.01. And EN cut specifies the cutoff energy we are using in this simulation. And NSW means the number of maximum iteration in ionic relaxation. So if we are doing relaxation where the ionic positions are changing, then we can specify the maximum iteration of ionic relaxation. Or in molecular dynamic simulation, this is the step we are calculating. And IBR ion indicate relaxation mechanism. So here 2 means conjugate gradient method, I think. And ISIF means how we are relaxing the system. So here is the table. So for example, if ISIF equals 3, then we are calculating force and stress tensors and also relaxing ionic positions and changing cell shapes and changing cell volumes. So this corresponds to full relax. If you want to know what these text and what these numbers means, you can check FASP homepage. So if you search FASP, there is FASP homepage, website, and there is documentation and online FASP manual. So here you can find almost everything about those texts. For example, if we find ISIF here, ISIF tag. So here is the table you saw before. And also there's some information about files. So for example, if you see postcard file, then it explains the format of postcard files, how it is written. So if you're curious about those informations, you can find more information on this manual. So first, let's run our first calculation. So we will be using the cluster, and we will be submitting queues of our jobs using this qsub command. So here batch.j file contains the job information, so what we are be doing and how much resources we are be using. So we prepared this batch file, so we can copy this file, and using qsub command we can submit the job, and using qstat command we can monitor our how our jobs are going. And then we can see how calculation is going using this tailf command on OCG car or std out or out car. So let's first try this calculation using this in car and this kpoints file. Okay, so if you have calculated fast, then if you write tail out car, the tail command shows the last part of the file. So if you write tail out car, then you can see these timing informations. So in this case, this calculation took only a few seconds. And also we can see the kpoint information in IBG kpt file. So this is irreducible Brilliant-John kpoint file, and this file contains the kpoints in irreducible Brilliant-John. So in kpoints file, we specify 3 by 3 by 3 grid. So that will be 27 kpoints. But here, we only calculated 4 kpoints. That is because the diamond silicon system is highly symmetric, and many of them are duplicate. So it can be reduced into 4 kpoints inside irreducible Brillouin zone. So we need to calculate only 4 K points instead of 27. So there are Contka file as an output file. So Contka file is in the same format as postcard. So it contains lattice information and ionic positions. So this is the position and lattice at the end of the simulation. So we did relaxation calculation. So this is the relaxed lattice parameter. So it is different from postcard file. And there is also file called OSGI car. So this file shows the electronic and ionic relaxation information. So here, we can see that at first ionic relaxation, we went 11 electronic relaxation to find self-consistent wave function. And then in the next ionic relaxation, we went only 4 electronic relaxation. And the next, we went 4 electronic relaxation, and the ionic relaxation ends here because we reached the relaxed position. Since we have already calculated charge density and wave function at first ionic relaxation, the second and third electronic relaxation just need a small changes, and it took much smaller steps. So here we can see its energy changes and other informations. So here so we can get the energy information from AUCA file. So if we use this command, grep command, so grep command is a command that finds some text inside the file. So if we write this command, free and 2 space after free, AUCA, then it finds this text in the AUCA file and print that line. So we can see these 3 lines. So the first line corresponds to the total energy, the free energy of system at first electronic relaxation, and energy at second electronic ionic relaxation, and energy at third ionic relaxation. So the final system energy will be this last energy. And we can also find energy during electronic relaxation, but that does not give much information. So if we write this command, this means we save this output of this command into the file named energy.dat. Then we can see it is saved into the file, and we can use this file to plot energy versus step. So if you have GNU plot, then you can write GNU plot, and then inside the GNU plot you can use this command. So plot energy.dat file using the 5th column. So as you can see, the energy is at first, second, third, fourth, and fifth column. And we are plotting this with line and point. So if you write this command, you can see graphs like this. And there are very many information on AUCA files. So if you have time, you can look inside the AUCA file and see which informations are there. So now we will do some convergence test. So as you learned in the previous lectures, the energy of a system depends on cutoff energy and k-point sampling. So when cutoff energy is high, the energy is more accurate, but we need much more time to compute. And same for k-points. So we need to find some points where the calculation has reasonable time cost and also accurate enough for our purpose. So for example, in order to do that, we usually calculate energy changing cutoff, for example. So first, we calculate energy at 400 eV, then 450 and 500, and then we can obtain this curve. And you can see which cutoff energy is appropriate by setting some convergence criterion. So in general, we use energy per atom is the change in energy per atom is smaller than 0.01, so 10 milli electron volt, and pressure is smaller than 10 kilobar, and force is smaller than 0.02 electron volt per angstrom, something like that. But this criterion can be changed depending on which property you are calculating. So if you are calculating, for example, phonon, you need to be very accurate on force. So you can use much strict criterion on this force. But in general, this criterion is fine. So so let's do some cutoff energy convergence test. So in order to do that, we need to calculate the energy of a system changing the cutoff energy. So we need to do multiple calculations. You can do it manually by changing EN cut in in-car and run simulation, and change EN cut again and run simulation again. But you can also write some script and do it automatically. So for example, this is the shell script which calculate cutoff energy, which calculate energy of a system while changing cutoff energies. So you don't need to know what all this means, but what this do is it iterates for cutoff energies in 250, 300, 350, etc., and change cutoff in the in-car as a specified cutoff and run facet calculation and grab energy from the out car and append the cutoff and energy to cutoff.dat. So you can just do it manually. So this is just for convenience. So this script is inside this batch underbar cutoff.j file. So you can just copy this file, batch underbar cutoff, and submit job using qsub command. So let's do some convergence test. So calculation takes some times, but so the result looks like this. So at cutoff energy of 250 electron volt, the energy is this, and at 300 electron volt, energy is this. So we can plot the energy versus cutoff energy. So it will look like this. So as the cutoff energy increases, the energy converges into specific value. So so if we want our energy to be accurate, as the energy per atom is change in error in energy per atom is smaller than 10 milli-electron volt, then we can see that the 10 electron volt per atom is like this. So here we have 8 atoms, so the total energy difference will be 80 milli-electron volt. So as you can see, if we use 250 electron volt, the error is above 10 milli-electron volt per atom. But if we use 300 electron volt, then you can see the error is smaller than 10 milli-electron volt per atom. So we can use 300 electron volt as a cutoff energy. So we don't need to use 600 electron volt, but we can use much smaller cutoff energy and be accurate enough. So here we can say that cutoff energy of 300 electron volt gives converged results. And the same thing applies to K points. So in principle, we have to sample all infinite number of all K points in the first Brillouin zone, but because we can't, we have to sample some K points to represent the entire Brillouin zone. So as we increase the number of K points, the precision, it will be more accurate, but the time cost will increase. So time cost generally proportional to the number of K points. So we need to test the convergence against the number of K points. So for example, in this K points file, we are using Monk-Horst-Peck grid with 3 by 3 by 3 grid. So if we change this 333 to, for example, 111, 222, 333, and 444, and then we can see the convergence of energy versus the number of K points. So this is same as the testing convergence test of cutoff energy. So we will not do this calculation because it takes some time. But you can just copy this file and submit this batch file to submit your job. So here, similarly, we are changing cutoff K points, number of K points in one direction, 2, 3, 4, 5, 6, and we write that information into K points file and then run simulation and get energy information. So you can do it manually by changing these numbers in K points file and run simulation and get energy, and change this K points file again and run simulation again and get energy again. So if you do this calculation, similarly, you can plot the energy versus the number of K points in one direction. So, for example, in this case, we can say that the 444 K points, 4 by 4 by 4 K points grid gives converged result because it is within 10 milli electron volt error per atom. So in this diamond silicon system, we can use cutoff energy of 300 electron volt and 4 by 4 by 4 K points grid. So now we obtained the converged K points and cutoff energy. Then we can calculate some properties of the system. Here we are gonna calculate lattice parameter of same system, diamond silicon. So we can do it in a two way. The first one is manual calculation. So here we are gonna calculate a set of fixed volume calculation. So we first set the volume of the system inside postcard file, then calculate the energy while not relaxing the cell parameters. So the volume remains same, but ionic positions may changes. Then we can obtain the energy, and we change the volume, then we calculate the energy again. And we change the volume again and calculate energy. Then we can obtain data points like this. So if you have these data points, we can fit, for example, Birch-Monaghan equation onto these data points, and then obtain the equilibrium lattice parameter and the energy at that equilibrium lattice parameter. So this is similar to the convergence test in the sense that we are doing same calculations while changing some parameters. So here we are changing the scale parameter, scale factor inside the postcard 0.97, 0.98, 0.99, and 1 to 1.03. So if you open postcard file, there is a scale parameter. So if this is this scale parameter is multiplied to lattice parameters and the position of atom ions. So if we set this to 1.1, then it is the same cell, but the volume is changed. Volume is multiplied by 1.1 to the 3, because this applies to lattice parameter. The volume changes is power of 3. So we can do the same simulations, same calculations by just changing this. For example, if we want to do manually, change this scale factor to 1.01 and then do calculation. Like this, and then grab the energy of a system. So you can write this energy and then change the scalar parameter again, and so on. So you can manually calculate this, but we prepared some automatic scripts that calculate energy while changing the volume of the system. So you can copy this file into the current directory and submit the job using qsub command. So if you run the script, then you will see in energy underbar volume.dat file the lattice parameter, the scaling factor, and the energy of the system. So you can draw this energy versus volume plot. So here you have to multiply the scale factor by the lattice parameter and power it to the 3. So if you plot this, it will look like this, and you can fit this Birch-Monaghan equation into these data points. So you can use many programs such as MATLAB, or you can just fit this inside GNUplot too. So if you write start.power file and write this, and write these commands into GNUplot, then you can obtain these final fitted parameters. So here you can see the equilibrium volume is 163.621. So this is the one way to calculate lattice parameter, and there is also other way to calculate lattice parameter. This is the calculation we first did. So here you can just use write NSW to proper value, and then write Ivorion equal to. So Ivorion equal to means you are gonna do some relaxation using conjugate gradient, and write ISIF equals 3. That means you're gonna change not only ionic positions, but also change cell volume and cell shapes too. And then if you run this simulation, the simulation will automatically relax the cell into cell parameters to its equilibrium value. One thing to notice here is that you will need to use cutoff energy higher than the converged value. For example, 1.3 times the converged cutoff energy. This is because there is something called play stress. This is artifacts that comes from the basis set. So since we are using plane wave basis set, if the cell volume changes, the basis set also changes. So this play stress comes from that. So we will have to use much larger, not much larger, just small, slightly larger cutoff energy. Then you can check the final lattice parameter from the Contka file. So we will gonna stop here, but there's also other examples such as hafnium oxide and kappa. So you can run this simulation if you are interested. Thank you.
Thank you for your effort. So he was the Dongson Yu, or Yu Dongson, one of my students, and okay, thank you. And so how is it going there in UT side? So everybody is catching up, or okay? So
some of us finished the job, but the others are not
Okay, I think there is some difference among the students. Okay, so I suggest you to take the time and follow the steps one by one. This lecture material is pretty much self-contained, so I'm pretty sure that you can follow them one by one by just copy and paste of the info files. Okay, and so and if you have any questions, then please leave a note to me or from the email, or I think maybe the Professor Watanabe can collect the some of the question sheet among the students and maybe ask me collectively. So any kind of the contact is fine for me. And the rest of the examples are pretty much similar to the previous one, and so I think you can also follow them step by step. So okay, so we're gonna have the 2 weeks of the break and then come back to here after 3 weeks. It's pretty long time, so I suggest you everybody here to repeat or try something new, new things on the similar data files. Okay, so thank you for your attention and see you 3 weeks later. Okay, bye bye.